So here's one where graphing it is not necessarily as straightforward as most of the ones we've seen. They're all functions that you should know, or functions that you know exactly a function you should know. You could be able to move it around with easy transformations. Y equals 1 over x squared, of course, is such a function. So we're going to put our parabola there first. Oh my God, that looks terrible. All right, that doesn't look that much better, but close enough, right? But now what about this 32 over x squared plus 4? I don't expect you to know what that means and what it looks like, so I would expect you to use some kind of graphing tool to graph something like that. I'll show you real quick something that we can do. If I put in x equals 0, obviously I get 8, so I know that it's there. And something that might come in, will come in handy in a little bit. You know, these things all have very similar shapes. So I will say 32 over x squared plus 4, similar shape to 1 over x squared plus 1, which you probably don't really know what that looks like either off the top of your head. But if you graph that, it's one of these humps, right? So it's doing something like this. It's supposed to be symmetric. Wow, what I graphed was not symmetric. It's supposed to be, you know what? Next time I'll just draw it on Desmos because this looks crappy. But you know very well from calculus that this guy is going to go as x goes to infinity, this guy's going to go to 0 from both sides. So it kind of looks like that. So this is similar to a previous example where this is symmetric. So even though it's asking me for this whole region, I can probably do 2 times 0 to whatever the intersecting point is. And again, I can use my integration with respect to dx, right? So this is y equals x squared, and this is y equals 32 over x squared plus 4. Okay, so clearly, if I write my approximating rectangle here, my bigger guy is the hump here, and my smaller guy, what happened there? This would be y, no, I'm doing y2 minus y1. Okay, fine, whatever. I was doing this, y2 minus y1. Symmetric, so do 2 times area from 0 to intersection point. All right, so let me write that, what I just wrote, what I was just talking about. Just let's set up our area real quick. Area is 2 times the integral from 0 to I don't know where. The top curve is going to be the 32 minus x squared plus 4. And then the bottom curve is going to be x squared dx, right? So I have to just find that intersection point. So I'm going to set them equal to each other. So 32 over x squared plus 4 equals x squared, or x to the fourth plus 4x squared equals 32. So minus 32 equals 0. This is not bad. This is not one of these crazy ones where you have to like guess and check, because you see this is actually a quadratic, right? It's quadratic in x squared. Meaning if I do let z equals x squared, this turns to z squared plus 4z minus 32, which we can immediately factor. Now, in Calc 2, I don't bother to write this typically when we have these. I would immediately just do it this way. And then 32 is going to be 8 times 4, so plus 8 and minus 4. Okay. All right, so I would just go straight to that. You can certainly go through making the substitution explicit if you want. Usually if I do one of those, I'll write it in the margins like that. Now, clearly x squared is never equal to -8, so this first one doesn't give us anything. This guy, x squared minus 4, gives us two solutions, x equals plus or minus 2. Okay, now, in this particular example, unlike the one with the absolute value, there really is no significant difference between going from 2 times 0 to 2 or going from -2 to 2. It would there's no, I mean, the integral is the same and everything. So it doesn't really matter. I just kind of did the thing out of habit using the symmetry. One is a little bit nicer because at the end you have one of these guys where you evaluate 0 rather than -2, so maybe a little bit less opportunity for error. So for me, that's good because you know I can't add. Okay, now we get to the meat of the problem. The meat of the problem here is now I have to integrate this buddy. And how do I integrate? So integrate x squared, we know how to integrate that. That's not the problem. The question is, how do I integrate 32 over x squared plus 4? Okay, because that is not something that u substitution is going to work with. Well, I mean, in the end, yes, but the way it's written, it doesn't look great, right? So forget what I said. What we want to do is looks like 1 over x squared plus 1, right? Which we know integrates to inverse tan, right? And because we know that inverse tan, the derivative of that is 1 over x squared plus 1. Sorry, I had a little bit of a mix up there. And so I just rewrote this a little bit better. So in the process. So exactly, we know that if we got this to look like 1 over x squared plus 1, I'd be done. And it almost does. It's just there's too many numbers. Like, who needs these numbers, right? We do need the numbers. We won't have the right answer. But we can massage this to look like we want, and then we can integrate it. That's the idea. It's important to go through this so that you're familiar with this as an idea. So easily to get the 1 on the top, we just pull out 32, no problem. Now to get the 1 in the bottom, that is to get 1 in the place of the 4, what we have to do is force factor, basically. Basically, we're pulling out a 4. So that would give me x squared over 4 plus 1. So pull out a 4, right? Because if I pull a 4 from there, if I multiply this 4 back through here, I'll get x squared plus 4. So basically this is force factoring. All right. And now what do I have? This just becomes 8. And then what do I have here? X squared over 4. This is actually x over 2 quantity squared plus 1. And then I can let u be x over 2. And then I have this 8, but basically I have u squared plus 1. And this is my friend that I can integrate easily, right? So we just moved some of the constants around, and then we're going to use our u substitution. Okay, so let's use that. Let me see if I can grab this, put that down here. Okay. Come on, what? All right. I don't know what that was. A mess up is what it was. But now you can see what we can do here. I don't need that substitution for the x squared. So maybe just to make my life easier, I'll just break this up into two things, right? This would be 8 times 1 over x over 2 squared plus 1 minus 0 to x squared dx, because I certainly don't want to substitute in for the easy integral, right? So now, I don't even do it that way. Okay, so if I do my substitution, I've got 8 times 1 over u squared plus 1, because I let u equal x over 2. Then du is 1/2 dx. So dx is going to be 2 du. So I'm going to get a 2 du here. And then when x equals 0, u equals 0. So that's 0. And then when x equals 2, u equals 1. So that's 1. All right. And then this guy is going to go over, sit here, go along for the ride. Okay. Now, the first one is super easy now because I'm not even going to rewrite it. This is 16 times this guy, which is just going to be inverse tan of u. So I have 16 inverse tan of u going from 0 to 1. And then this is just going to be x cubed over 3, x going from 0 to 2. Okay, and of course, you don't need to write that there. I wrote that there to keep myself clear what variable is doing what. Okay, you can also change back to x and use your original ones, whatever you like. All right, so what do we have here? 2 times 16 inverse tan of 1 minus 16 inverse tan of 0 minus 8/3. Yes, minus 0. Okay. All right, so inverse tan of 0 is 0, right? And inverse tan of 1 is pi over 4. That's the thing you should know. Okay, so this is 8 pi minus 16 thirds.